Now we will find speed and tension in vertical circular motion at different positions. Consider a particle of mass m tied at the end of a string and drilled in a vertical circle of radius r. As shown in this figure, consider A is the highest position in VCM, B is the lowest position in VCM, C and D, these are the mid positions in VCM. At highest position, that is at point A, let V1 is the linear speed of the particle at point A, and at point A the weight of the object or the particle is acting vertically downward, that is mg, and let T1 is the tension in the string when the particle is present at the highest position, that is at point A. Now when the particle is present at the lowest position, that is at point B, the weight mg is going to be acting vertically downward and tension in the string, say T2, which is towards the center of this circular path, and let V2 is the linear speed at the lowest position at point B. Similarly, at point C, that is at mid position, at point C, consider V3 is the linear speed at position C and V4 is the linear speed at position D. Now at highest position A, we have assumed V1 is the linear speed and T1 is the tension in the string. But we know that the resultant force which is going to be acting on a particle which is performing vertical circular motion at any position is given by the equation T minus mg cos theta is equal to mv square upon r. So for the highest position, this T, that is tension, we can write T is nothing but T1. This V, it is nothing but V1, and in VCM we assume the particle starts from this ground point, that is lowest position from B, then the particle will move from B to C to A, so it makes an angle of 180 degree, so therefore theta is equal to 180 degree. Now we are going to substitute this value in this equation, so we are going to get this T1 minus mg cos 180 is equal to m V1 square upon r. Now we know that cos 180, that is minus 1, therefore we can write T1 minus it becomes plus mg is equal to m V1 square upon r. Therefore T1, which is nothing but the tension at the highest position in vertical circular motion, is equal to m V1 square upon r minus mg. So this equation gives us the tension at the highest position in vertical circular motion, that is at point A. Now we want to find the minimum velocity of the particle at highest position. Finding minimum velocity at highest position A, it means the particle which is performing vertical circular motion, it must possess the minimum velocity at highest position such that the particle will just complete or just pass from that point and complete the vertical circular motion. But when the particle is present at the highest position, then we can see the mg, which is weight of the particle, and tension T1 in the string, both are in the same direction. And for finding the minimum speed at the highest position, we are going to consider the tension T1 is equal to 0. Even though the tension T1 in the string is 0, then also the particle is able to complete the vertical circular motion, because in this case the required centripetal force is provided by the weight of the object itself, and the motion is going to be in such a way that the string should not be slack. It means that string should remain straight and the particle will just complete or just pass from point A. So we are going to put T1 is equal to 0 in this above equation. So we are going to get 0 is equal to m V1 square upon r minus mg. We will rearrange the term. So therefore we are going to get m V1 square upon r is equal to mg. This m will get cancelled with this m. Therefore, we are going to get V1 square is equal to Rg. Therefore, V1 is equal to under root Rg. So this is the equation which gives us the minimum velocity which must be possessed by the object at the highest position to just complete the vertical circular motion without any slack in the string. If velocity of the particle is less than the prescribed value, then tension becomes zero, and due to which there will be slack in the string and vertical circular motion is not possible. Now at lowest position B, we have assumed that V2 is the linear speed at point B, T2 is the tension in the string. But at point B, as we can see, the weight of the particle or object mg, it is acting vertically downwards, and tension T2 in the string, it is directed towards the center of the circular path. As we know that the resultant force acting on the particle performing VCM at any position is given by the equation T minus mg cos theta is equal to mv square by r. So from this figure we are talking about lowest position B. We can see here T is nothing but T2, V we have assumed it as V2, and theta is going to be 0 degree. Because we have assumed the particle starts from the lowest position, that is from point B, so theta is going to be 0. Now substituting these values in this equation, so we are going to get this is T2 minus mg cos 0 is equal to m. This is V2 square upon r. Cos 0, that is 1. Therefore we are going to get T2 minus mg is equal to m V2 square upon r. Therefore T2 is equal to m V2 square upon r plus mg. This equation gives the tension at the lowest position in the vertical circular motion, that is at point B. Now for finding the minimum velocity of the particle in VCM at the lowest position, we are going to make use of law of conservation of energy, because in this VCM there is an interconversion of kinetic energy and gravitational potential energy. Therefore, according to law of conservation of energy, we can say that total energy at A is equal to total energy at B. Therefore, we can write total energy at A is equal to total energy at B. Therefore, this we can write it as kinetic energy at A plus potential energy at A is equal to kinetic energy at B plus potential energy at B. So for kinetic energy at A, we can write it as this is half m at point A, it is nothing but V1 square plus potential energy at A, that is mgh. Here as we have assumed B is at the ground level, so and OP is the radius, so we can clearly see that when the particle will move along the path BCA, it means the total upward distance traveled by the particle from B to A, that is r plus r, that is 2r. So height in place of h we are going to put this is nothing but 2r. So mg 2r is the potential energy of the particle when it is present at point A, is equal to kinetic energy at B, that is half m at B. This we have assumed at V2, so V2 square plus potential energy at B, that is mg, and as we have assumed that particle B is at the ground level, so in place of h we can put 0. So therefore here we are going to get this is nothing but half m. Now V1, we know that V1 it is a linear speed at the highest position A, and its value we are already knowing. The value of V1, that is linear speed at the highest position, is under root Rg. So here we can add this nothing but root Rg square. We have substituted the value of V1 plus this we can write as 2mgr is equal to half m V2 square plus 0. Therefore this we can write it as mgr upon 2 plus 2mgr is equal to 1 upon 2 mv2 square. Now we are going to multiply with 2 on both sides of this equation. Therefore we are going to get mgr plus 4mgr is equal to mv2 square. 4mgr plus mgr, we are going to get this is 5mgr is equal to mv2 square. This m will get cancelled with this m. Therefore we are going to get v2 square is equal to 5gr. Therefore taking square root on both sides, we can write v2 is equal to under root 5gr. This is the equation for the minimum velocity of the particle at lowest position in vertical circular motion. Now at mid position, that is at point C or at point D. At point C, as we have assumed, V3 is the linear speed of the object and T3 is the tension in the string. We know that the resultant force acting on a particle performing VCM at any position is given by the equation T minus mg cos theta is equal to mv square upon r. Now from figure we can see this tension T here. T we can put it as T3 for point C, tension in the string, that is T3. V, that is linear speed, V is nothing but V3. So for this V we are going to substitute this V3. And for this theta, from B to C, the total angle made over here at the center, it is 90 degree. So we are going to put theta is equal to 90 degree. Now by substituting all these value in above equation, we are going to get T3 minus mg cos 90 is equal to m v3 square upon r. Now we know that cos 90, that is 0. So we are going to get T3 is equal to m v3 square upon r. So this is the equation for the tension when the particle is present at mid position, means the particle may be present at point C or at point D. For both the points, because both the points are at the mid position, the tension is going to be T3 is equal to m v3 square by r. Now for finding linear speed at point C, means at the mid position, we are going to make use of law of conservation of energy. Therefore we can write total energy at B, total energy at B is equal to total energy at C. So we are going to compare these two. So therefore we can write kinetic energy at B plus potential energy at B is equal to kinetic energy at C plus potential energy at C. So for kinetic energy we can write this is nothing but half m at point B, V is nothing but V2 square plus potential energy, that is mg, h as we have assumed be at the ground level. So for h we can put 0. So this is 0 is equal to kinetic energy at C, that is half m at C, velocity that is v3 square plus potential energy at C, that is mg, and h is nothing but the when the particle is moving from B to C, it covers a distance, that is r is the total height. So we can write this is r. Therefore we are going to get this is 1/2 m v2. It is a speed at point B, and we know that at the lowest position the value of v2 it is under root 5gr. So here we can write this is nothing but root 5gr ka square. So this is nothing but v2, we have just substituted the value of v2 which is root 5gr plus this is mg into 0, that is 0 is equal to half m v3 square plus mgr. Therefore we are going to get this is nothing but 5 mgr upon 2 is plus this is 0 as it is equal to this is mv3 square upon 2 plus mgr. Now multiplying both sides of this equation with 2, therefore we are going to get this is 5 mgr is equal to m v3 square plus 2 mgr. We will shift this 2 mgr to this side. So here we are going to get 3 mgr is equal to m v3 square. This m will get cancelled with this m. Therefore we get 3gr is equal to v3 square. Taking square root, we can write v3 is equal to under root 3gr. So this is the value of velocity at point C of the particle which is performing vertical circular motion. As point C and point D both are at the mid position, this v3, which is the velocity of the particle at point C, is going to be same at point D, which is root 3gr. So these are the values of the minimum velocities of the particle which is performing vertical circular motion at different position. At highest position, that is at point A, the minimum value of velocity, it should be v1 is equal to root gr. At lowest position, that is at point B, v2 is equal to root 5gr, and at mid position, that is at point C or at point D, it is root 3gr. From this we can clearly see that as the object is moving in upward direction, that is along B to C to A, its speed goes on decreasing. Here it is root 5gr, here it is root 3gr. At the highest point it is minimum, that is root gr. But when the particles start moving in downward direction, that is along the path ADB, its speed goes on increasing. That is here at the highest point it is root gr, at mid position it is root 3gr, and at the lowest position it is root 5gr.